Now let's see the next question. What is my next question over here? My next question is explain bias variance trade-off. This is also a very good fundamental questions which you can expect in the interview. So what is bias, what is variance, and what is this trade-off? So bias variance trade-off is a key concept in machine learning that describes essentially the balance or the trade-off between two model parameters. One is the biasness, which is attached with the model, and the other is variance. Let's try to understand that what bias means, what variance means, and then probably we will be able to do a good job at that, right? Like once we understand bias and variance, then we will be able to understand it appropriately, right? The trade-offs between them. Let's jump over here. So let's see, we have a model over here. Okay, and my data is, so this is my, let's say my y, and this is my x. It's a one feature. Okay, and my data is, let me draw some data. Okay, I think which fits. Okay, this is the sort of data which I have. Okay, this is the sort of data which I have. Now what I will do is, and let's see our, it's a regression problem, and we have to do we are doing a linear regression sort of thing. If we are doing a linear regression, then my first, I have to fit a straight line, okay, and fit a straight line, and then try to see that, okay, how good the performance of this model is. Let me see that if I am able to fit, let's say we fit this particular straight line, right? And we calculated the MSE, and this is the best MSE which we got, right? Based on this linear line. So the assumption is that this data is distributed linearly, so I am fitting a linear line. Is it doing a good job of it? I don't think it's doing a very good job, right? Because the data is spread across. It's clearly not very linear sort of data, right? So this kind of model, right, would be, okay, let's hold that thought over there, okay, and let's name it that first model. Okay, now let's see another one. Okay, over here, let's see, we did a fitting of a polynomial fit, right? And the polynomial fit is like this, right? This is my number 2. Okay, let me remove a couple of data points. Okay, this is the polynomial fit. Okay, this is number 2. Now I can, and this is a polynomial fit of degree. What will be the degree? This looks like a parabolic, so it's quadratic with polynomial degree 2. Okay, let me try to fit another one over here. I'll select another, probably yellow. Okay, let me try to fit another one over here, and this time I try to fit the data, all the points of the data. Okay, so I did something like this, and this is my third. Okay, and this is a degree of n, maybe n is greater than 5 or something, right? To fit this data, it looks like it has to be a higher degree polynomial. Okay, now let's see, we have 3 models, 1, 2, and 3. Okay, which model does the best job of fitting the data? Okay, now obviously you will see that the model 3 has best fit this data, right? But is it the best model? Now here comes the concept of bias and variance. My first model is doing what it is doing? It is doing underfitting. Why it is doing underfitting? Because it is not capturing the essence or the distribution of the data itself. The data is clearly not linear, but it is trying to fit a simple model on a data which is more complex. So we'll call model 1 as high bias. Okay, we'll call model 1 as high bias. Now let's see, that is the concept of bias, that you are not understanding or you are oversimplifying the data distribution. then the model which will come out of it will be considered as a high bias. Okay, high bias. Now take the model 2. The model 2 is doing a better job, right? It is fitting almost all the data points also, and the degree is only 2, right? So this probably will be lower bias, low bias than this, because it is trying to at least capture the essence of the data distribution. Okay, this will have a low bias. The number 3, we will just see that whether it has a high variance or low variance. Let's see. The number 3 model is fitting the data as it is, right? But if there is a new data point which comes tomorrow, let's say a new data point which comes tomorrow, which lies over maybe over here, will it do a good job of doing the prediction? No, it will not do the good job of doing the prediction, because it will not be able to generalize well. What it is doing over here, it has something which is called high variance. When we call high variance, if the model is overfitting, it is overfitting. Why it is overfitting? It is capturing the data distribution and the noise also. Why the noise? Because all this data is generated through some system, through some tool, and that may not be inherent data distribution, but that may have carrying some noise also, and it is capturing all the noise because it is going through all the data points. That's why it is called high variance scenario or overfitting scenario. When it is overfitting, it will not generalize well on the new data points. Okay, it will not generalize well on the new data points, and that's why this is the case of high variance, low bias. The bias is very low. Why? The bias was high in which case? In model number 1. Why? Because it was not capturing the inherent essence of the data distribution. Here it is capturing way over. The number 2 model is probably with a degree of polynomial of 2, is low bias and relatively low variance also, right? Because it will be able to capture the data, or it will be able to generalize well on the newer data sets, right? So it is called the scenario, and in this particular case, the case may be different in different data sets, but in this particular case, it seems that the number 2 is doing a better job, and we should go for something which has low bias and low variance, right? Relatively low bias and low variance. Okay, so this is the concept behind your bias and variance. Let's see. So now we know, friends, that the bias is something which represents the error that occur when a model is too simple, right? Like model number 1, a straight line, too simple. It is underfitting. On the other hand, variance represents the error that occurs when a model is too complex. Model number 3, it is overfitting, right? What is the goal? So this underfitting and overfitting, by now you must have understood that it's a trade-off. Once we increase the degree of polynomial, it will go from high bias situation to low bias, and low variance to high variance situations, right? It will go in that. So that is the thing which is called trade-off, and you have to find the optimum value of your model where the bias and variance are both low or relatively low. Okay, that is the sweet spot which you should be targeting for. So the goal of the machine learning is to find a model that generalizes well to the newer data. Okay, so a balance has to be maintained between bias and variance. Okay, I hope this is clear. Now let's see this with an example also over here. This may be, in our case, this is the MSE, mean square error of our model, right? Regression model. And this is the model complexity. This you can assume as the model complexity is something like the degree of polynomial. So you started with a straight line, degree 1, and then degree 2, and with degree 2 with the parabolic or quadratic, and then degree 5 or 10. Let's see on the x-axis, we are denoting it like that. In this case, what will happen? What will happen? If you see over here, we'll start with a very simple linear model. We'll be in the area. The green line denotes the validation or the test error, and the blue line denotes the training error. Now let's see what will be the training error and the test error in this case. If I am doing a very simple model like a linear model, it will be the case of high bias, right? My error will be very high. Both the training and the test, both the training and the validation, both error will be high. Why it will be high? Because I am not capturing the inherent data distribution itself, the essence of the data distribution I am not capturing. So it will be both high in this case. As you are increasing the degree of polynomial, right, the bias will keep decreasing, the biasness will keep decreasing, okay, and your error will keep going down. Why the error will keep going down? Because now you are fitting the data more properly, okay, you are fitting the data more properly. Your error will keep going down, okay. In case of training error, if you keep increasing the polynomial, okay, you keep increasing like from polynomial 5 to 6 to 7 to 8 to 9 to 10, your training error will keep fitting the data more and more appropriately, and it will capturing the noise also. So for the performance metrics or the error which you'll receive from your training data for a higher degree polynomial will keep going down, keep going down, and ultimately it will come close to zero. But for the same model, what will happen for the validation or the test set? It will not generalize well. The higher degree polynomial is capturing the noise. It has high variance. It will not generalize well, and your validation will start going up in the high variance area, right? Okay. So friends, I hope this particular diagram captures the essence of bias variance trade-off very, very well. Okay. So what is the sweet spot where my bias is not so high, my variance is not so high, and the way to figure that out is that where my training and validation error are both low, that is the area, that is the point where I should keep my bias and variance trade-off as fixed. Okay, so in this particular case, probably this region over here you see, right? After this region, validation error, if you increase the degree of polynomial, the validation error will start going down. Training error will keep going down, but the validation error will keep going up. So this particular is the sweet spot. Okay, and you should be targeting for whatever model complexity is over here. And in our case, it was the quadratic or degree of polynomial 2. You should try to capture that particular error. Okay, so this is the concept behind variance, bias and variance. Okay, now there are concepts in machine learning you must be knowing that how do you figure this out, right? You figure this out through cross validation. So model complexity will one of the hyperparameter, and you can tweak or tune that hyperparameter to arrive at this, right? Basically, you are testing your model with different model complexity and drawing it. Okay, so there are concepts like regularization also. Okay, you start with a higher degree polynomial, or you start with a more complex model, and then you regularize that. When you regularize that, then that means you are increasing the biasness of this. You are making the model more simpler from complex, right? That is the concept of regularization, and those are the things which are used in machine learning to arrive at a correct level of bias and variance, and that's what bias variance trade-off is. Okay, friends, I hope this is clear. Okay, let me know in the comments if there is anything else which is left.